Can everybody hear me up there? All right. All right, so I see a lot of people are not here today, which means it's a great day to take attendance. So we'll do that. Thank you. And last time we kept talking about NP-completeness. Cook's theorem, we proved satisfiability is NP-complete. Everything in NP reduces to a polynomial time. We reduced satisfiability to graph colorability using a gadget-based proof. Clauses became these equivalent of OR gates, and arbitrary Boolean formulas became graphs that are three-colorable if and only if the Boolean formula has a satisfying assignment. So if you have a solver for graph colorability, you can solve Boolean satisfiability. So by Cook's theorem, all of NP reduces to satisfiability. By this theorem, all of satisfiability reduces to graph colorability, which means by composition of these two reductions, graph colorability is NP-complete. In particular, three graph colorability is NP-complete. How many understand that? Good. Any questions about that? We sort of went through that last time in greater detail, and that's just a summary. So we left off by asking ourselves, what about colorability is really that hard? Because certain things, if you reduce the parameters of the problem enough, it makes the problem easy. It makes the problem trivial, in fact. So 0-degree graphs means that there's no edges there. So obviously every 0-degree graph is three-colorable. In fact, every 0-degree graph is one-colorable, not just three-colorable, because there's no edges. So you don't have to worry about graph colorability constraints. So that's trivial. Now, 1-degree graph, max-degree 1 graphs, you can only have pairs, not even cycles. So if you have pairs, at most 2 colors are necessary. And certainly every 1-degree max graph is 2-colorable, never mind 3-colorable. So that's easy too. 2-degree graphs, max-degree 2 graphs, those are either cycles or long lists, chains of nodes. That's max-degree 2. You can't even have a tree because that's max-degree 3, your parent plus your children. So that's 3-colorable. In fact, it's even 2-colorable as long as there's no odd cycle. How many remember that or believe that? Good. So that's easy too. So graph colorability is NP-complete for max-degree 4 graphs. We're about to prove that. So at 0 and at 1 and at 2, easy polynomial time algorithms, almost trivial. For degree 4, it's NP-complete. So at 4, this is where this parameter, when set to 4, computational complexity explodes for this problem. Different problems, different parameters, different thresholds. So now we're exploring the threshold of intractability in the graph colorability problem. Notice I deliberately left out max degree 3. For extra credit, you tell me if max degree 3 graphs are is an NP-complete problem for colorability. Okay, so the idea here is similar to the previous proof. We're going to use gadgets to reduce the degree from 4 to at most 4 if it's higher than 4 anywhere in the graph, and then show that that version of colorability is just as hard as arbitrary version of colorability, where the degree could be anything you'd like, arbitrarily high. So we introduce this gadget here, and this gadget is a piece of graph that has the following properties. The max degree here is 4, and you can tell by just counting the degree everywhere, and it's 4 over here in the circled nodes. Here it's 2 and 2 and 2, so max degree 4, that's the easy part. It's 3-colorable, but not 2-colorable. It's not 2-colorable because it has triangles. A triangle is already not 2-colorable. It's an odd cycle. It requires 3 colors because every node touches every other node in the triangle. So 3 colors are necessary as well as sufficient for a triangle. So it's not 2-colorable, but it is 3-colorable. How do we know? Here's a 3-coloring. So there's a 3-coloring, and there's other 3 colorings as well. Here's the least trivial of the 3 properties. Any 3-coloring of this gadget leaves all corners with the same color. Any valid 3-coloring must have all 3 corners, the outer corners of degree 2, all have the same color. Here's why. You can think about a diamond as a three-colorability constraint propagation device. So if you're going to three-color a diamond that looks like this, 4 nodes, not quite a clique because one edge is missing, with a crossbar across the diamond, if you paint this node one color and this node another color, the third node must acquire the third color, right? That's because it's a triangle. So these 2 nodes constrain this node to be neither one of those. But these 2 constrain this last node to be neither one of these, which means it'll be the same color as the opposite node that we started with, the red one. So it'll be red over here. Now, if this started out blue, this will be blue because the colors are interchangeable. You can call them red, blue, and green, but you can call them also color 1, color 2, color 3, or color alpha, beta, and gamma, or whatever you'd like. So how many get that? So one tip of the diamond constrains the other tip to be the same color as itself. All right, now having done that, you can sort of keep in mind now that opposite sides of this diamond like this, wherever it's some piece of the graph, in any three-colorability valid coloring, these 2 nodes here are correlated. In fact, they're not just correlated, they're identical. Okay, so here comes the gadget again. Let's see what happens here in this gadget. So the middle color has to be something, so we'll call it red arbitrarily. If you don't like red, make it blue. But whatever color that is, you'll see that that color propagates out to the opposite ends of these 2 diamonds, because there's a diamond right here, the same diamond as this. And we already showed that opposite corners must have the same color. Well, these are 2 opposite corners of this diamond here, and these are 2 opposite corners of this diamond here. And so this red propagates to these 2 opposite corners. Those must acquire the same color as the middle red color. How many get that? Okay. Next, things begin to be more constrained now, because these 2 colors cannot be red. So they can either be blue and green or green and blue. But because this is bilaterally symmetric along the vertical line, it doesn't matter if you make this blue and this green, or this green and this blue, just flip it around and both cases are identical. How many see that? Okay, so without loss of generality, we'll make this blue and this green. But now everything begins to be very highly constrained. This red, this blue must induce this to be green because it's got to be different than the red and the blue that are both its neighbors. And this is a valid 3 coloring. So similarly here, this blue, this green and this red must force this to be blue. That has no choice. Now if this is blue and this is green, they both must force this to be red yet one more time. And now there's the third property. All opposite corners of this gadget must have the same color. Okay, good so far? We're not done with the proof. We're going to use this gadget that now has these properties as a lemma in the larger proof, showing that max-degree 4 graphs colorability is NP-complete. All right, so here comes the big idea. We're going to use these gadgets as node replacements. And this gadget has these 3 properties, but so do multiple copies of the gadget. So here's the gadget that we showed the last slide. Here we painted the corners blue, not red, but same difference. Opposite, all the 3 corners must be the same color. In fact, the same color as the middle node, the blue here. Now let's copy this gadget one more time. And this double gadget has the same properties as before. How many can see that? It's 3 colorable, but not 2 colorable, right? And opposite, the corner nodes, this node, this node, this node, and this node must all acquire the same color as all of each other, right? Because they're connected by the tip, which is the same identical node for both gadgets. And so these blues propagate across multiple copies. So if you make one more copy and connect it like that by the tip, all these nodes, all these corner nodes, these edge nodes, must all have the same color as each other by the similar property that we have in the previous slide. These colors propagate. So these properties are inherited from the single copy of the gadget to multiple copies of the gadget. So again, it has max degree 4. It's 3 colorable but not 2 colorable, and in any 3 coloring, all corners get the same color. So whatever 3 coloring you induce on this super gadget, it's multiple copies of the regular gadget, all these circle nodes must get the same color. In fact, they must get the same color as these nodes also, the middle nodes of all 3 and the connecting nodes. But let's not worry about those. I want to focus on the corner nodes that have degree 2. You'll see why in a minute. Okay. So the idea is that we're going to use these supernodes, these super gadgets, as fan-out components to replace high-degree nodes with low-degree nodes in such a way that preserves three-colorability. And once we do that, amazingly, the graph will become max degree at most 4, and it'll be three-colorable if and only if the original graph was three-colorable. So here's a replacement strategy. Let's say you have a high-degree node. In this case, high means bigger than 4, so let's say it's 5. So we're going to take this node of degree 5, and there's lots of other nodes around. I'm just focusing on this particular node of degree 5. And what's happening here, I'm going to replace that node. Here are all the 5 edges that come into this node, but now I'm going to remove that node and replace it with this gadget. So here's the gadget here, replacing that original node just like that. It's a local replacement strategy. And what I'm going to do is connect these 5 incoming nodes to the tips, to the corners of this gadget. Okay, and now this whole local area here, replacing the original node by this gadget, has max degree 4, because these edges are only connected to the tips, to the corners, and these corners have max degree 2, and adding one more edge to them will give it max degree 3, not even 4, and the degrees of anything else is not increasing, so the max degree here locally is 4, but all of these edges coming in sense or experience the same color constraint as if they came into a single node like they did before over here. So this gadget preserves the colorability constraint of the rest of the graph. The rest of the graph doesn't know that it's a different graph now locally here with this replacement. How many get this strategy? Good. That's a lot of you. So we keep doing this. We keep replacing any high degree node with these gadgets. And once you do that, you get a new graph whose max degree is no more than 4, but has the property that it's three-colorable, even only if the original graph was three-colorable. So here's an example. I'm copying this graph over here. Here are the problematic nodes of degree more than 4. Here's degree 6. Here's degree 5. So I'm going to focus on this node of degree 5, or 6 in this case, the green node. And I'm going to do what I did on the previous slide. Replace this node, eliminate it, replace it with this super gadget, and there's the gadget. Super gadget. Now it's deformed a little bit, but that's okay. It's just topological, so deforming a topological graph doesn't change it. It's all about connectivities, not locations of nodes. And then these edges incoming, instead of connecting to that middle node that's now gone, it's going to connect to the tips, to these edges of this gadget. So here's now the local replacements of all of these edges. This edge will connect to here, this edge will connect to there, this edge will connect to here, this edge will connect to that node of the gadget, and this edge will connect to this tip of the gadget, and so on. And I can make as many copies, as large a gadget as I need to accommodate a larger and larger degree there locally. I just make more copies of the little gadget in the super gadget, and I can handle whatever degree I want. And I do the same thing for this node here, which has degree 5. So here again, I'll put the gadget in, do the little local replacement of the blue node by this replacing gadget, and then connect all these nodes here to the tips. Now I have a new graph, and a new graph simply replaces high degree nodes with low degree gadgets, and the rest of the graph doesn't change. If the degrees are lower elsewhere, it doesn't change, but the max degree now drops to 4. And this new graph is three-colorable if and only if the original graph was three-colorable. So if I had a three-colorability solver that could only handle max degree 4 graphs, I can exploit it in this way to solve colorability for arbitrary graphs. And that's pretty much the proof. Right? So solving max degree 4 graph colorability is as hard as solving any colorability, which means it's NP-complete. We reduce all of NP to max degree 4 colorability instance. So what's the complete reduction of all of NP to max degree 4 colorability? First, Cook's theorem, of course, is always in play. All right, Cook's theorem reduces every arbitrary non-deterministic polynomial time computation to a satisfiability instance. And satisfiability reduces to 3 satisfiability. 3 satisfiability we already saw to reduce to graph colorability. And here we're reducing graph colorability to graph max degree 4 colorabilities. All these, 5 reductions or 5 transformations composed together give you a reduction of all of NP to max degree 4 graph colorability. How many understand that part? Okay, any questions about that? And the whole thing is polynomial time. Why? Because each component of this composition of reductions was itself polynomial time reduction. So a polynomial composed with a polynomial composed with a polynomial and so on, as many finite times as you like, still gives you a polynomial. Of higher degree perhaps, but polynomial nevertheless. So this is a polynomial transformation of all of NP into max degree 4 graph colorability. And we already saw that max degree 0 or 1 or max degree 2 colorability are trivially solvable in polynomial time. So this is where colorability explodes into full bloom intractability at degree 4. Okay. Any questions about this proof? Yeah.
This is specific to free colorability, right? What about other numbers of colors?
Excellent. So he's asking, what about other numbers of colors for 2 colorability or 5 colorability? So what if I ask you if a graph is 0 colorable? How hard is that? Let's find out why 3. I ask you if a graph is 0 colorable. What's an algorithm for that? Is any graph 0 colorable? Actually, technically speaking, there is a graph that's 0 colorable. Technically, it's a boundary case, right? Empty graph, having no nodes. So if you have no nodes, you don't need any colors. Okay. But if a graph has any nodes at all, even one node, 1 color is necessary, not 0. So it's not completely trivial. You got to ask yourself, is the graph empty or not? That's the equivalent. That's easy to do with one if statement, right? Okay, 1 colorability. A graph is 1 colorable if and only if what is true? No edges whatsoever. You can have as many nodes as you'd like, but no edges, it's 1 colorable, good. So that's a very simple algorithm again. 2 colorability, we're getting more and more complicated, because 3 colorability, you know how that goes. That's NP-complete. So what about 2 colorability? What's that? No odd cycles. Even cycle is okay. Even cycle 2 colors, right? Color 1, 2, 1, 2, 1, 2, 1, 2, 1. So you can color an even cycle with only 2 colors. But an odd cycle, like a triangle, requires 3 colors. Think about it. But a cycle will never require 4 colors. So a graph is 2 colorable if and only if it has no odd degree cycles. That's a little bit more tricky to determine, but you can still do it in probably linear time if you're careful. 3 colorability now, the next one, NP-complete. So that's why we harp on 3 colorability, because that's where colorability explodes at 3 colors. Now, why not 4 colorability and 5 colorability? That will be the next question. So is 4 colorability, 5 colorability, NP-complete? Short answer, yeah. What do you say?
I mean, I would presume that if you can use this reduction strategy for arbitrary colorability down to 3 colorable, and 3 colorable is NP-complete,
Yeah, so short answer, yeah, they're all NP-complete for larger than 3. I'll leave it up to you to convince yourself or convince me, maybe for extra credit, that this is true. It's not hard to argue that. But any larger than 3, NP-complete. Smaller than 3, polynomial time solvable, obviously. Yeah.
What about the 2 colorability, though? You said as long as there aren't any odd cycles, but I mean, there's no guarantee that the graph is going to be only of degree 2. What if you have this big monster of a thing that has, 10-degree nodes sprinkled throughout the whole thing, and it just happens to be 2 colorable anyway?
That's okay, but when we're saying a graph is 2 colorable if and only if it has no odd cycles, so here's an algorithm to generally 2-color a graph if a 2 coloring exists, okay? Take an arbitrary node, color it with the first color, color 1, call it color 1, so we don't harp on green and blue and red. Color 1 on an arbitrary node. All of its neighbors must acquire color 2 now, because they're connected to this color 1 node. All of their neighbors must be color what, if it's 2 colorable? color 1 again. They have no choice because they can't be color 2. And we're trying to conserve colors. So we're going to reuse color 1. Their neighbors, again, the uncolored neighbors of of those nodes must be the other color. The colors are alternating, basically, starting from an arbitrary node. If you succeed in coloring the graph in this way and there's no clashes, you're good. The graph is too colorable, you're done. If at any point there's a clash, you try to color a node with the alternating color, and one of its neighbors is already that color, no good. In fact, at that point, you detected an odd cycle, if you think about it, because it went around and created an odd cycle. So it's just general characterization. We're not saying the graph is only odd cycles and nothing else. It could be arbitrary complexity, but if there is an odd cycle, it's not too colorable. And if it's too colorable, they can't be an odd cycle. It's an if and only if. So the condition for two colorability is the existence of any odd cycles, no matter what the rest of the graph looks like. And I just gave you a pretty straightforward linear time algorithm to find the two coloring if one exists. Equivalently, the algorithm determines if it is an odd cycle or not by the same reasoning. So I hope that clarifies things. There's a question, yeah.
So why is it okay to pick an arbitrary starting point? If you pick something like in the middle, work yourself to the
So he's asking another good question. Why is it okay for this algorithm to start at a random starting point, arbitrary starting point? What if you start somewhere else? Won't you get potentially a different result? What do you guys say to that?
Because the most you can get, there are only two possible end results you can get, one coloration or its inversion with all the colors switched around.
Yeah, because color 1 and 2 are interchangeable. So if you picked another starting point and it wasn't color 1, swap the names of colors 1 and 2, and now it's equivalent to the, if you started somewhere else potentially. Because there's only two colors and they must alternate, and two neighbors can't have the same color. So that node, wherever you started from, has to be one of the two colors. So put one or two colors there, and you're just as good as if you started somewhere else, and you keep propagating from there. It's like when you find connected components in a graph. It doesn't matter where you start. Or more subtly, if you do minimum spanning trees in a graph like prim or Kruskal, again, it doesn't matter where you start in prim. You still will get the minimum spanning tree. Of course, the minimum spanning tree might not be unique, but that's okay. You'll get a minimum spanning tree. But it's a good question. You've got to think about, what if you start somewhere else? What if you pick the wrong place to start? Question. Infinite colorability? So do you ever need infinite number of colors for a graph? What kind of graph will require an infinite number of colors? If a graph has a finite number of nodes, if a graph has n nodes, what's the maximum number of colors you can possibly require, even if it's a complete graph and n nodes? N colors, right? So it won't be more than the number of nodes. If every node gets a different color, you'll never go wrong. You'll never have a conflict with your neighbors. Right? Now, not all graphs are finite. There lies a catch. But in this course, we're not concerned with infinite graphs. If we did, it'd be a different kind of course, actually. Yeah. If you think things are subtle with regular graphs that are finite, don't even ask me about infinite graphs. Let me give you examples of infinite graphs. Take all the points, take all the integers, make them all nodes. Already we have a countable infinite number of nodes, one for every integer. Connect every node to every other node whose integer difference is less than 10. So every node will connect to, 5 or 10, I guess about 20 nodes, right? Like, for example, the node 10 will connect to 0 through 9 and to 11 through 20. So all node will connect to all other nodes that are 10 away or less as integer values. That's an infinite graph. How many see that? Okay. How many colors are required to paint this graph, to colorize this graph? Not so obvious, right? And if every node was, if it was the complete graph on all these nodes, one per integer, how many colors are required if it was the complete graph on countable number of nodes, one for every integer? How many colors are required? countably infinite number. So there's an infinite, but that's an infinite graph. Let me give you another infinite graph that even has more nodes than this. So how many nodes is it going to have? Uncountable number. Make every point in the plane a node, literally. All uncountable number of points in the real plane, make them nodes in the graph. Can you do that? How many say you could do that? Yeah, I just did that. I mean, of course you can do that. Whatever you define. Yeah. Connect every node in this graph to every other node that's less than 1 unit away. There's an infinite graph with infinite number of nodes, infinite number of edges. Uncountably infinite number of nodes and uncountably infinite number of edges. What's the chromatic number of this graph? That's not obvious at all, actually. In fact, some of these kind of questions are open problems. We don't know. For example, this particular graph I just named, I think it's known that the chromatic number is between something like 4 and 7, but we don't know which. Question?
There was actually a result last week that it's between 5 and 7.
Between 5 and 7? Oh, okay. So somebody improved it to 5, the lower bound.
That 4 is impossible.
Yeah, good. So there you go. And between 5, 6, or 7 for that particular graph, nobody knows still. If you can figure it out, probably a PhD right there, and a very nice paper, because it's been open for probably many decades, this particular problem. So let's back off from infinite graphs. So I just gave you like a little exposure to infinite graphs, and somebody asked about them or alluded to them by asking the question, do infinite number of colors are required? So you can have plenty of infinite graphs, just not in this course. Probably much to your relief, I imagine. What other questions might I answer at this point? Yeah.
Is there any particular reason you constructed those gadgets using that particular configuration? Is it possible to make them simpler?
Well, the gadget has to have these properties to make it work. It needs to kind of have a bunch of nodes be forced to have the same color, so all the incoming edges sense or feel the same color no matter where they're connected to in the gadget. And they got to be connected to different points in the gadget to keep the degree low. Because if you're all connected to the same point, the degree will blow up at that point. So I'm trying to keep the degree low. So the gadget kind of spread out the degrees. Now, how did somebody come up with this gadget that has these properties? A lot of head scratching and soul searching and trial and error over probably many weeks or even months of hard thinking. It's a pretty clever proof, actually, if you think about it. Somebody had to come up with this gadget, realize the gadget has these properties, and that it makes it work in this proof, and that the whole thing kind of hangs together nicely, and the result is shown. It's not an accident. It's very deliberate, very intentional, and quite clever, if you think about it. All these NP-complete proofs are very clever, and some are so clever, it takes hundreds of pages to describe them. I'm not kidding. Some people's entire PhD thesis was one giant transformation of some kind like this, but taking not just 2 or 3 slides to describe like we just did, but 100 or 200 slides or pages to describe. And then you have to prove all the lemmas, why it works and how it works and why it does not, fail to work in certain cases. And, it's a big mess, but it kind of hangs together. It's just a lot more complicated. Yeah.
Well, specifically, I asked because why can't you just take out those 5 nodes in the middle, replace it with just 2, just one red, one green, and then connect each of those to the other 4 points?
And here's why you can't do that. He's saying, why not have 2 points here, connect these 2 to one and these 3 to the other, and connect the 2? Well, you tell me, why will that fail here? I mean, it's a good question. Yeah.
Does that not guarantee a max-degree?
Well, you could guarantee the degree of 4 by having 2 nodes here. These 2 will connect to one. These 3 will connect, or these 4. That's it. These 3 will connect to one. These 3 will connect to the other, and the 2 nodes will be connected to each other. So you'll have 3 hanging off here, 3 hanging off here. The degree will be 4 and 4, and the 2 will be connected to each other. That's sort of what he's saying. So the degree will still be 4. That part is okay, but something else will fail. What will fail? Yeah, what do you say? The colorability constraint will fail, because these 2 nodes will be different colors. So these 3 incoming edges will be connected to a green node, potentially. These 3 incoming edges will be connected to a blue node, And because they're connected to different colors, these constraints don't propagate out to the rest of the graph like they did before, and it's a different colorability for a different kind of graph, and it's not anymore. So this new graph is no longer 3 colorable if and only if the original graph was 3 colorable. The if and only if part failed, or potentially could fail if you do this. But this gadget preserves the property that all incoming edges all connect to same color nodes inside this replacement region. And so therefore, whatever happens for the rest of the graph is equivalent to whatever happened to the rest of the graph too, having one node with one color. So this gadget operates as a single atomic node. There's atomicity here going on. It behaves as an atomic node even though it's a gadget and composed of lots of nodes. It behaves as if it was a single node with a single color. And that's important. Because if it didn't, the rest of the graph could all of a sudden do other things that it couldn't do before on the left-hand side in the original graph. How many get this subtlety? I mean, you got to do something like that to make it work. You can't just make arbitrary replacements, creating an arbitrary new graph that has no relation to the original graph with respect to colorability constraints. You have to maintain the colorability constraints of the original graph precisely, no more and no less. That's a very good question. It's a subtle question, right? What else? Now, let me ask you another question. Could there be another gadget that works just like this gadget, just looks differently and is much bigger, it has more nodes and edges and still does the job? How many say, yeah, you probably could, yeah, you'd probably find something. In fact, if you use larger and larger gadgets here and leave some of the tips in the corners unconnected, that will still work. Just create larger and larger version of this same gadget and just don't use the rest of the gadget, just use some portion of it. Or you can have a whole new gadget altogether, right? You can also close this gadget on itself and connect this to that and make it completely kind of close as a loop. How many see that? That will work too. Just use more bigger gadget and have more kind of 2-degree nodes, have enough of them for the connectivity to the outgoing or incoming edges, whichever way you want to think about it, and that will work. So there's plenty of ways to make it work, but there's even more ways to fail to make it work. Right? Just like any math problem has lots of ways to solve it, but lots more ways to solve it badly or solve it wrongly, right? As you already know from solving problems in this class. So other things could work, but many things won't work. And it's cleverly constructed and designed to make it work. You know, it's not easy to do, right? What else? Because we're about to see probably an even more subtle proof than this. We're going to show that even if you make the graph planar, planarity of graphs makes them very restricted. What is a planar graph, by the way? I don't want to be presumptuous. A graph is planar if and only if what is true. Take a wild guess just from the word planar. What do you think that means?
The graph will fit in a plane.
Yeah, it'll fit in the plane. You can put it in the plane so no 2 edges cross. So you put all the nodes wherever you want, and then you draw the edges in a way that will make it work. Now, not every graph is planar. In fact, most graphs are not planar. So if I have there's a famous kind of children's riddle that has, you want to connect, 3 homes, I'm going to not draw them very well, and to 3 utility companies, like water and power. So, you want to connect it to water, and you want to connect it to power, and you want to connect it to, phone service like landlines, but I'll just draw smartphones. And anyway, you want to connect all these 3, each one of those 3 to those 3. So it's a graph. It's a 3x3 bipartite graph. So the graph is a K3-3. Right? So how do you do it? Well, the first node is easy. You can connect the first house to all 3 utilities like that. Second node, it's a little more constrained. You connect this one to here, right? Connect this one to the second utility going the long way, and you can connect it, to the first utility going the long way, and you can connect it to the second utility going the long way over here, right? This node, you can connect to the first utility going the long way, and to the second utility going the other long way. But guess what? Now you're trying to connect this node to that utility, ain't going to happen. And in fact, you can prove that there's no way to do it in general. So K33, the complete graph, and complete bipartite graph on 3 nodes, 3 and 3 nodes. Bipartite means the nodes are partitioned into 2 parts, and every node in one part is connected to every node in the other part, and vice versa. So it's like the complete graph, but instead of having one group, you have 2 groups. So everything in one group is connected to everything in the other group, and vice versa. That's the bipartite, 2 parts, bipartite graph on 3 nodes. So bipartite graph on 3 nodes and 3 nodes, K33 is not planar. Some edges will cross. There's no way to embed it in the plane without edges crossing. It turns out also that K5, the complete graph on 5 nodes, is also not planar. And the complete graph on 5 nodes looks like this, right? And it turns out there's no way to embed that in the plane without edges crossing either. So those are the 2 culprits, K5 and K33. And there's a famous theorem by Kuratowski saying a graph is planar if and only if it doesn't contain as subgraphs a K5 or K33. Okay. That's a complete characterization. That's not easy to prove, by the way. So the maximum nodes a planar graph can have is roughly 3n. The maximum number of edges. So if you have 3 nodes, you can have at most 3 edges. If you have 4 nodes, the 4th node can connect to all the previous 3 nodes. So now there's 3 more edges. The 5th node can connect to all these 3 again on the outside, but not on the inside. So there's 3 more edges again. The 5th node can connect again to all these 3. So every time you add a node, you add 3 more edges. It turns out that's the best you can do. So the total number of edges in a planar graph is 3 times the number of nodes at most. Now it could be less, but it ain't going to be more. So that's another theorem. You just can't fit too many edges before you run out of room to add more without crossing previous edges. How many get that? Okay, so that's a couple of theorems about planar graphs. Now, so planar graphs are very highly constrained, right? So because they have no more edges than 3 times the number of nodes, they're not general graphs. General graphs can have a quadratic number of edges in terms of number of nodes. N choose 2, which is roughly quadratic, right? It's n over 2 times n plus 1. So many graphs are not planar. So what if you just talk about colorability for planar graphs? Is that any easier than arbitrary general colorability? Because we already saw if you reduce one of the parameters of the problem low enough, the problem trivializes. So if you reduce the max degree to 0 or to 1 or to 2, it becomes easy. But 3 is still hard for degree constraint. So what about planarity? Because other families of subgraphs that are even more constrained than planar graphs become easy again. I'll give you an example. Colorability for trees, just trees. Trees are graphs. Graphs are not necessarily trees because they can have cycles. Trees are graphs without cycles. So if I give you a tree and say, is it 3 colorable, what's your algorithm? That's an easy problem. So if you're thinking too much, you're probably going the wrong way. But I'm asking for a polynomial time algorithm. So, but I appreciate people speaking up because a lot of people are very quiet. And it's not great. Yeah.
Bleed down the tree.
Yeah. Paint the root one color. All of its children the next color. All of their children the first color again. Alternate. Color 1, color 2, 1, 2, 1, 2, 1. As you keep going down the tree, breadth first. That'll paint the graph with 2 colors, and it'll always succeed. How many see that? What if it's an unoriented tree and you're not sure where the root is? Not a trick question. Again, it's an easy question. You can pick any node to start with, just like before. Right? It doesn't matter if you pick the root. If there's not sure what the root is, this will work if you pick any node at whatsoever. Start with any node in a tree, paint it color 1. All of its neighbors are color 2. All of their neighbors are color 1, 2, 1, 2, 1, 2. As you keep expanding from that one node, this will still work and paint the entire tree using only 2 colors. You'll never get an odd cycle situation that requires 3 colors. Why won't you reach an odd cycle? Again, a trivial question. Because there ain't no cycles, much less I'd say it's a tree. There are no cycles in a tree. So you don't have to worry about odd cycles. So colorability for trees is trivial. And trees are 2 colorable. Any questions about that? Yeah.
You had to specify in the second case that it was neighbors and not children. Or node is not the root node.
Sure. So instead of saying children, let's just say neighbors more generally, because now it's not oriented in any particular direction. There's no up or down. It's just out from the node. Yeah, good point. But the same algorithm is still valid there. Right? You keep going out from the node and breadth first search, and you keep alternating the colors. Okay, so the moral here of the story is that if you restrict the graphs enough, 3 colorability becomes trivial. In fact, some families of graphs like trees become 2 colorable, never mind 3 colorable. By the way, if a graph is 2 colorable, it's also 3 colorable. How many understand that? Yeah. If it's 3 colorable, it may not be 2 colorable, but if it's 2 colorable, it's 3 colorable. Somebody can prove that with one sentence. If a graph is 2 colorable, it's also 3 colorable. Don't use the third color. Or, let's say we force you to use the third color. How are you going to use it? Use 2 colors only, and then pick an arbitrary node. Use a third color for that one node. You're good. There's no conflict because nothing else has that color except that last node. So if you really are forced to use a third color, sure, you can use that too, but you don't have to. Okay, so if you restrict graphs to a certain subfamily, with enough constraints on the structure of the graph, yeah, it becomes trivial. So the question is, if the graph is planar, is it trivial or is it still NP-complete? It turns out it's NP-complete, right? It says so right there. How do you prove such a thing? They're about to prove that colorability is NP-complete for planar graphs. It's not obvious at all. Because all the graphs that we've seen so far were not planar, right? Here there's an edge crossing right there, even though they may not have to be in some other planar embedding. If you look at these graphs that we saw, with satisfiability reducing to color, this graph is not planar. Look at all these edges crossing here and here and here and here and here and there, and all over the place there's edges crossing, right, potentially. So what if you restrict the graphs to be planar? Then this proof will certainly fail. This proof does not show that planar graphs are NP-complete. Colorability of planar graphs. How many understand that? Because this is not a planar graph over here. If you restrict to planar graphs, you couldn't do this proof, and maybe colorability for planar graphs is easily solvable, not NP-complete. We're about to show it's NP-complete. It's as intractable as can be in the class NP. So we're going to use a planarity preserving gadget. So here's the gadget that we're going to use now. It's more complicated than the last gadget. It has more nodes. There's more going on here. But the properties are similar. It's planar. Obviously, it's planar. There's no edges crossing. It's 3 colorable. There's a 3 coloring, and there's other 3 colorings. And in any 3 coloring, opposite corners get the same color. So this corner and that corner must have the same color, and separately, this corner and that corner, 2 opposite corners here, must get the same color as each other, but not necessarily the same color as the first pair of corners. They can be independent. Here, they happen to be the same. Both are red. But it could be blue also. So I'm giving you an example here where these 2 are blue and these 2 are green. We're about to prove why this is true. So let's take it one step at a time. So let's say you're trying to show that 2 opposite corners get the same color. The middle color here is arbitrary, because you can call it red or you can call it color 1. It doesn't matter. So make that red. And its 2 neighbors are the other 2 colors. And because it's highly symmetric, it doesn't matter what these 2 are, green or blue and green, because If it was the opposite, just flip the whole thing around and keep going. How many get that? So without loss of generality, assign them the other two colors. But once you do that, things become more constrained. Because remember the constraint propagation of diamond-shaped subgraphs. One corner, one tip of the diamond propagates its color to the other via this color constraint propagation that we mentioned a few slides ago. So we're going to apply this construct here as a lemma, right? So here we have a diamond. These four are on a diamond, so this green induces this node to be green as well because they're opposite sides of a diamond. How many see that? The diamond is sideways. It doesn't matter. It's topological. It doesn't matter which way it's oriented. Here's another diamond now. So this blue constrained this one to be blue, right? And now this node can be one of two things. It can't be blue because there's a blue neighbor. So it can be red or it can be green. So let's assume it's green and later we'll chase the red option separately. Because here we can't do it without loss of generality because it's no longer symmetric. So let's say this is green. But now this is green, this is blue, so this must be what? Red, right? And by the way, here we're going to chase down the other option, making this red instead of green. Well, we'll do that separately. So this one is red now, so we'll make that red. And this is red and this is green, so this has got to be what? Blue. Good. Now you're getting it. And the colors keep propagating around. So this must be now red, because these are green and blue, its neighbors. This one must be what? Green. Has no choice. It's all forced now, all the way around the periphery. So blue and green must make this what? Red. And this must be blue. And the last one? Red again. Good. So notice what happened, that this was green and this was green also. And this was blue and this was blue also, but this only assumed that we made this green instead of red in the original choice. So now we're going to chase this guy down. So after we finish this, we're going to chase this one down. And here are all the color propagation constraints. These two constraints will be green. This got to be blue. This has got to be red. These two constraints will be green, red, blue, and finally red again. So these are the only two valid three colorings, given that the middle was red, and the middle, without loss of generality, was red because it could have put anything there, and the same thing would happen. So if the middle was blue, these four will be blue. How many get that? So, because the middle color then gets propagated out to all four ends in a way that opposite corners get the same color. So we just proved that the second property, the B property here, is preserved, no matter what the three coloring is. All right? So notice also I'm emphasizing again, the opposite corners are independent. In other words, this will be the same color as that, and the other two will be the same color as each other, but independently of the first pair. So they can either be green, green, blue, blue, or green, 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 green. And in this case, they're red, 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 the same as each other, but they don't have to be. They could be independent. Okay? This is important, actually, this property. Otherwise, I wouldn't be highlighting it for you like that. All right, so now we're going to use this gadget as a replacement strategy like we did in the previous proof. And we're going to say, whenever you have an intersection, like here and here, and by the way, let me just say as an aside, this graph is depicted with a non-planar embedding. In other words, some edges crossed, like right here and right here. There's crossed edges. But it's still a planar graph given another embedding that is planar. So planar graphs can have non-planar embeddings, but it doesn't make them a non-planar graph. I'll just say that and leave it at that. But let's say we didn't know that, and we want to get rid of these two intersections and do planar graph colorability decision on whether this graph is three-colorable, but we only have a decider for planar graphs. How can we exploit a planar graph decider to determine the colorability of arbitrary graphs that may not be planar? Well, local replacement is the answer. Take these two crosses where they cross, and take this graph and move it over here, and then replace these crosses with these gadgets. So again, it's a gadget-based local replacement strategy. So take this cross here and replace it with this gadget instead, and the incoming edges will be diamonds this time because they preserve the opposite corners of the diamond to be the same color constraint. So for example, this edge here will be replaced with a diamond like that. Because if this is blue, this is blue. And if that's blue, the opposite corner of his gadget is blue. And when this is blue, the opposite corner of this diamond is blue. And through this gadget, the blue propagates again. And so if this was blue, the blue propagates all the way here and then connects to whatever this connected before. And this edge gets you from a green to a blue, same as it did the long way here. But here, the blues kind of jump around in a way that allows you to make other things go across them the other direction. So here we'll have another diamond, and this green will connect to that green, which will make this green, which will connect to this red. So this green senses a red neighbor. Just like here, this green senses a green, red neighbor again. But these must be green. So the color constraints propagation for the rest of the graph, other than this local replacement, will still be the same in the original graph. And if the original graph was 3-colorable, this graph will be 3-colorable. It's an if and only if. And here we do the same kind of replacement strategy. Let's just finish it. Here's this diamond here. Here's the edge here. And this graph is 3-colorable if and only if the original was. How many can see that? Okay, good. That's a lot of you. I'm impressed. Obi-Wan has taught you well. Any questions about this? So we just proved that planar graph colorability is as hard as arbitrary graph colorability. So colorability is not difficult because of the planarity or non-planarity of the graph. It's just hard in general, even for planar graphs, for a very restricted class of graphs. Now, if you restrict the graphs enough, like we said earlier for trees, that's obviously 3-colorable. In fact, trees are 2-colorable. We mentioned that 5 minutes ago, 10 minutes ago. So somewhere between trees and planar graphs, the problem explodes in intractability. NP-completeness goes full bloom on you. Somewhere between the simple class of graphs that are trees and the slightly more complicated graphs that are planar graphs. But you don't have to go to general graphs to get this phenomena of intractability to explode. It happens somewhere between the two. Any questions about that? So it's interesting to find these thresholds where a problem becomes hard. Why? Because in real life, you may be asked to solve a problem. Traveling salesman or all sorts of other intractable problems, scheduling and binning and packing and knapsacks and Steiner trees or whatever. And then you may want to stop and ask, yeah, the problem is hard in general. It's NP-complete. But that doesn't mean that specific smaller subclasses of it that are more constrained are still hard as the original problem. They may or may not be. You have to think about it. So if somebody asks you to solve traveling salesman for point sets, but it just so happens that all the points lie in the periphery of a circle, that might be easier to solve than arbitrary instances of traveling salesman. Because maybe the solution is all the points around the circle, and that's it, just in the order in which they appear around the circle. That most likely will be the solution if there's a lot of them. How many get that? So it's important to know where the threshold of intractability is. Even if you know if a problem is hard, ask yourself, is the instance that you have to solve for your job or your project or your company or your boss, is that instance still one of those hard ones in terms of the overall constraints? Or does it become easy, like graph colorability on trees, or 2-colorability on arbitrary graphs, and so on and so on, where there's much easier, simple polynomial time trivial algorithms. And it's good to be able to know the difference between one and the other. So this is almost like a sensitivity analysis of where intractability goes full out on you, and where the problem is simple enough that maybe intractability is no longer and something you need to worry about because the problem is easier. Even the halting problem, same thing happens there. The halting problem is easy to solve if your program doesn't have any loops, for example. How many get that? Sure, it will halt. Or if your program has loops, but the loops are all bounded by constants. It's I going from 1 to 1,000,000, not I going from 1 to k, some arbitrary variable. If the loops are all constant number of times, no matter how much they're nested with each other, that too will halt. How many get that? because it'll fizzle out eventually and run its course, right? So even for halting problem, there's large infinite classes of instances which are tractable to determine. They're not intractable. They're not undecidable. And the question is, what's the threshold at which this phenomena happens? It's important to know that. Because now you know what you're dealing with, and maybe you can solve it efficiently. Maybe it's not time to give up and tell your boss, oh, it's NP-complete, because your boss will then come to you and say, well, yeah, it's NP-complete in general, but the instances I asked you to solve are perfectly doable, and it's too bad if you didn't know that or didn't think about it. Okay, so graph colorability for planar graphs is as hard as arbitrary graphs. So let me ask you a question. What if the graph is both planar and max degree 4 at the same time? Because look, the max degree here wasn't necessarily 4. Yes, it was planar, but it wasn't max degree 4. So maybe if you put both constraints simultaneously, that it's got to be planar and it's got to be max degree 4 at the same time. Maybe that's easy. What do you say?
Your 4-degree gadget happened to be planar, so all you have to do is take, after you do the planar enforcement, all you have to do is then...
Yeah, exactly. You can compose these two reductions that we just saw the last 20 minutes together, and they'll work beautifully. So if you have a degree larger than 4 here, take that degree larger than 4 and use the other gadget that reduces the degree to 4 right there, and that'll get you a max degree 4 and planar graph 2. And solving that problem with both degrees in play is still as hard as solving the original when neither constraint is in effect. So again, just to show you how it works, take this graph, make it planar like we did before, and then take this high degree node right here and make another replacement like you did before with this other gadget, and you get this other graph, and now you have a planar graph with max degree 4 at the same time, and that's as hard as solving arbitrary colorability without any constraints at all. Yeah?
Isn't that not max degree 4 yet? Because your planar gadgets have degree 5 nodes in them.
Where?
The one that's to the left of the middle one, or to the right.
Oh, right. In fact, good question. I even put in the slide something about it. So here's the degree 5, 5, 5, 5, and 5. So what do you do there? It's not a hard question. You got to reduce the degree to 4. So,
More gadgets.
yeah, more gadgets, exactly. It's great when you can ask a question and answer your own question. It's called research, by the way. So that's good. So why didn't I draw all these gadgets over here? Because this slide will become very messy if I did, or this gadget will be really tiny over here. Either way, the point is you got to take these gadgets and replace them here, 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 and here, and then you'll be good. But it's easy to do. Now, let me ask you this. First of all, how many understand what we just did? We composed two reductions. Okay. Does the order of these two reductions matter? First, we made the graph planar, then we reduced the degree to 4. Could we have reduced the degree to 4 here and then invoke the planarity gadget on top of that after the fact?
No, because the planar gadgets cause high degree nodes when you
Yeah. So the order here is important. You had to do it in the right order. Or alternatively, what you could have done is, you could have done it in the other order. You could have said, okay, make it low degree first, and then put in the planarity preserving gadgets. But now the degree could be out of whack again, so now you have to do the other one again. That's okay. So you could have gone out of order, but you'd have to go back and maybe do the first one yet one more time. So you could have done it that way, but that's kind of wasted work. So, of course, it'll still be polynomial time reduction end to end. Okay? So any other questions about any of this? So you see this proof's getting more and more esoteric and more detailed, but you see the general idea. They build on each other, and you get more and more insights into the problem, the structure of the problem, and now you see, colorability is difficult. But it's not difficult because of the high degrees, and it's not difficult because of the planarity of the graph. It's just hard because there's lots of possibilities on how to paint nodes in general. So it's nice to know why the problem is hard and why it's not hard because then if you have simpler instances in your job, in your work, in your programming, in your projects in the future, it's good to know why the problem is hard, not just that it's hard, because you may not have to worry about it if it's not an issue in the instance that you need to solve. Yeah? No, you can do it in any intersection you want. So this local replacement that we're doing here, wherever you have an edge, two edges crossing, all you're doing is replacing that crossing section with the gadget internally here, and then the things outgoing from the gadget still go to the nodes that were the neighbors of this crossing region before. And it doesn't matter what these other colors are in those neighbors. In fact, the graph is not colorized to begin with. So keep in mind that when I give you a graph and ask you is it three colorable and so on, I'm not giving you a graph with colors on the nodes. I'm giving you a graph that's not colored at all. It's not colorized at all. The nodes are all blank nodes. And I say, is this three colorable? And you get to tell me if it's three colorable, or if I ask you for the three coloring, you get to assign colors to the nodes in a way that preserves the colorability constraint. So the graph that I give you as an instance of this problem is not colorized at all. It's completely uncolorized. I'm just showing you an hypothetical coloring here, this being blue, this being green, this being red, and so on. But that's not the instance that I give you. I give you an instance without any colors at all. You need to paint them onto the nodes. But the point is this: however you paint these nodes to make it work over here, the same color scheme will work here given these local replacements. And that's why these local replacements preserve the colorability of the graph or the non-colorability thereof. If this graph was not three-colorable, this graph wouldn't be three-colorable either. Remember this mapping F from A to B, how many remember that diagram, A to B with an F? This mapping needs to preserve membership. Yes instances must map to yes instances, and no instances must map to no instances. This mapping does it. So not only it must map colorable general graphs to colorable planar graphs, it must map non-colorable general graphs to non-colorable planar graphs. How many understand that? That's not a lot of you, so ask me questions. Yeses must map to yeses, but nos must map to nos also. It must preserve the property of the original graph, whether it's colorability or Hamiltonian cycle tour existence or whatever it is. It must map yeses to yeses and nos to nos. I'm not sure that point got across because I didn't see a lot of hands go up. Yeah.
Do we know if that planar gadget is optimal, or is that just something someone came up with?
Excellent question. He's asking, is this the best gadget you can do in terms of size or complexity of the gadget? Let's just say that this proof was originated in the 1970s, actually early 70s. If somebody came up with a smaller gadget that works as well, we would have been showing you that instead of this one. So it's a very good question. So this is the smallest known gadget that does this job. Doesn't mean that there might not be smaller ones that are also working, although so many years have passed and nobody really came up with a better gadget, and some people probably tried, like you just asked that question, and other people probably asked it too. Why make it more complicated when you can make it simpler? That's called Occam's razor, right? We talked a lot about that in the course. Simpler is better. So this is probably the best possible, given all the time that elapsed. It's not a proof, it's just evidence, probably that it's the best possible. Question?
Is the better gadget problem NP-complete?
Is the better gadget problem NP-complete? So that's a meta question. That's a good question. What do you think about that? Let's say we try to answer that question. How would you answer it? Yeah.
That has a finite complexity, so you can just travel.
Yeah. This gadget has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 nodes. And, some 20 edges or whatever, I'm not counting them. If there was a smaller gadget, it'll be one of those graphs that have less than 12 nodes and less than 20 edges. There aren't that many graphs with that property. And by the way, those graphs must all be planar. So that reduces their number even more. There's probably a few millions of those, maybe a few billions at most, but not at Google, obviously. So in algorithm, we try them all. For each one, test if it preserves those. It's easy to see algorithmically if those properties are preserved. They're very specific, easy to determine properties. So somebody probably did a brute force search on all millions of nodes, all millions of gadgets that are smaller than this, and the answer was probably no. But if you do this, it's obviously not NP-complete because there's only a finite number of combinations. It doesn't grow with anything, so it will take constant time, much less polynomial time, to determine whether there's a smaller gadget. Because there's only a few million cases, you try them all, constant time. Yeah, a million is a large number, but it's still a constant. It doesn't grow with n. Constants don't grow, much less grow with n. That's why you call them constants, because they remain the same. Yeah?
That brings up another question, because you just said that there are only millions of possibilities, but in that case, which is n? Is it the number of possibilities or the number of edges or nodes?
Well, it'll be the number of other alternative gadgets that are smaller than this gadget. So it'll be all planar graphs of less than 12 nodes. And there's not that many of them. Well, by not that many, I mean a few millions only, or however many there are. But it's not going to be 10 to the 20 of them, much less any hugely intractable number. Because remember, the edges can either be there or not be there. So if you have, say, 10 nodes, yeah, it's a bunch of nodes. How many edges can there be on 10 nodes? Well, 10 choose 2. 10 choose 2 is a few dozen, right? And a few dozen edges, each one of which can be there or not be there. And so that's 2 to the power of the number of edges at most. How many get that? Because an edge could be there or not be there. So it's 2 to the number of possible edges, which is the square of the number of nodes. So it's less than 2 to the few dozen. Well, 2 to the 30 is only a billion, roughly. It's a large number, but that's, and if you have a few dozen, maybe a dozen more will be, more than that, but it won't be trillions. And keep in mind that most of these graphs will be isomorphic to one another. So you don't have to test them all even. So using isomorphisms and, redundancy and, you could just eliminate large classes of these candidates for gadgets. They're not all uniquely different from one another. Right? Okay, very good questions. I'm glad you're thinking this way. That's how researchers think. It's nice. So, planar one-graph colorability is trivial. Right? We already said, if there's any edges at all, it's more than one colorable. Two colorability is easy. Again, we mentioned you can do alternating colors from some starting point. Three colorability is NP-complete for graphs. So by the composition of this thing, planar graph, three colorability, that's what we just proved composing these two things. Four colorability, turns out it's trivial again for planar graphs because it turns out every single planar graph is four colorable no matter what. That's the famous four-color theorem for maps. If you take a map and replace it with a graph where nodes become the landmasses and neighbors become edges, it turns out that's the four-color theorem that's been open since 1852 and finally solved in 1976, over a century later. So it's been an open problem in math, in graph theory, for over a century. And this proof, how many heard of this proof, the four-color theorem? Good, a lot of you. It's a very famous problem. And when it was solved, the US Post Office canceled stamps on envelopes by saying four colors suffice. So it's a rare occasion where the US Post Office stamps envelopes with a theorem. Our government used to be much smarter back then, So sorry about that. One day it'll be that way again, maybe, but one can only hope. Okay, so, but because of this theorem that was finally proven, it's trivial to determine whether a planar graph is four colorable. The answer is always yes. So that's not hard to determine. The theorem itself was really hard to prove. The proof for this theorem was thousands of pages, by the way. In fact, the proof had so many special cases that only a computer program can generate them all, and another program checked them all. So it was one of those strange theorems that no human ever verified by hand. It was just too many thousands of pages and thousands of special cases. So some mathematicians actually object to this kind of a proof, that only a computer program can generate the proof and another program can check the proof, because now it's not exactly a proof that a human can wrap their mind around. What can go wrong with a proof like that? Both programs, one program or both programs can have a bug, and then you'll never know, because it's so long and tedious and labor-intensive process of generating and checking that a human cannot directly see it or understand it. All you can do is try to understand the code and hope that it's not buggy, but now you have to prove that the code is correct. So now you have to have a meta-proof that the code actually does what you say it does, namely generates the correct proof, and that other piece of code verifies it. So some mathematicians don't like this. Ever since then, there was, let's say, about 1,936 different special cases were involved, almost 2,000 special cases. People over time reduced the number of cases necessary to only a few hundred, but that's still a lot of cases. Even to this day, there's no clean, beautiful, concise, easy to understand proof, for humans to understand. They just reduce the monstrous complexity of it to a little bit tamer level, but not tremendously. Question?
The degree and planar gadgets we just saw were for 3 colorability graphs. Are there similar gadgets for 4 colorability graphs?
You could, yeah. Short answer, yeah. You could do that. You could generalize it. Now, planar graph 4 coloring could be determined in quadratic time. These are theorems. We're not going to prove them here. I'm just giving you the results for your information. Planar graph 5 coloring could be determined in linear time. And graph planarity testing can be done in linear time. So you can test whether a graph is planar or not. If I give you an arbitrary graph, ask you is it planar or not, you can do that in linear time, it turns out. That's not an easy algorithm at all, but it can happen in linear time. It's a famous result from the 1970s by, I think, Lipton and Tarjan, or two very famous award-winning theorists. 4 coloring in a 3 colorable graph is still NP-complete. So if I give you a graph and tell you it's 3 colorable, and you don't know what the coloring is, you just know it's 3 colorable, and I ask you to color it, not even using 3 colors, but using 4 colors if you'd like, so it's even more lenient, that's still NP-complete, actually, amazingly enough. That's how hard coloring is. Now it turns out that on a torus, 7 colors are both necessary and sufficient. So a torus is a basically cylinder wrapped around. A torus is like a donut. You know what it looks like. It's like that. And of course, topologically, a torus and a teacup are the same topology, right? They just both have one hole going through them. So if you take this 7 regions here, 1, 2, 3, 4, 5, 6, and the yellow one on the corner is the 7, and you wrap it around like this, and then into a torus. So you wrap the opposite edges together and then opposite circles together. You get a torus. You can see the 7 colors are necessary and sufficient. Well, at least necessary, because every hexagon here will be neighboring all the other 6 hexagons. How many can see that if you fold this into a torus? Fold this piece of paper into a torus. Roll it up like you'd roll a cigarette. I assume you don't smoke, but still. And then 2 opposite ends rolled together into a torus. Every hexagon will be neighboring to all the other 6 hexagons, which means 7 colors are necessary. And on eBay, you can probably get cups like this that are painted. A cup is a torus, so they're painted 7 colors, where every color is a neighbor of all the other colors. So, these cups on eBay will make a fine holiday gift if your loved ones appreciate, 4-color theorems and NP-completeness. They're going to love this one. Here's a general theorem: how many colors a surface of genus G, this is the number of holes, requires. The formula is roughly the square root of G with these constants here. So for example, in a plane, 4 colors suffice. That's right there, because the plane has no holes in it. A torus, 1 hole, requires 7 colors, like this example, where 7 are necessary. Turns out 7 are also sufficient. That's harder to prove. For a double-hole torus, like 2 donuts fused together, turns out 8 colors are necessary and sufficient. For 5-hole torus, quintuple torus, 11 colors are necessary and sufficient, and that's a general theorem. So the number of colors necessary and sufficient grows as the square root of the number of holes in the manifold, the topological manifold, which is a generalized torus. Next time we'll talk about applications of colorings, and then we'll get into heuristics, approximations to NP-complete problems where you can't find the exact answer optimally, but you can find a pretty good answer, no worse than, say, twice optimal in very quick polynomial time over linear time. So we'll do some of that. All right? See you next time.
The infinite graph you said with a line and connecting integer difference of 10, it can be colored with 11. By alternating 1, 2, 3, 1 through 11, then 1 through 11, and so on.
Okay, that's good. Yeah.
I did that while you were talking.
All right, appreciate it. Good job.